All right. Get ready for a deep dive into Einstein's theory of special relativity.
Always a fun one.
It is, but, and here's the twist, we're going to be looking at it from a really unique angle today. We're going to explore this argument, and it's a fascinating one, that challenges how we usually think about special relativity.
Yeah, it's interesting. We often get so caught up in the what's of special relativity, like the time dilation, the length contraction, that whole idea that the speed of light is the ultimate speed limit.
Right.
But this physicist, Robert A. Close, he really makes us think about the why. Like, why do these things hold true?
I like it.
His paper, it's titled, and it's a good title, The Other Meaning of Special Relativity. It really makes you rethink everything you thought you knew.
Okay, so let's unpack this a bit. Just a quick recap for anyone who maybe hasn't thought about this in a while. Special relativity basically says that the laws of physics are the same for everyone moving at a constant speed. Doesn't matter how fast you're going.
Exactly.
And that the speed of light in a vacuum is always constant. It's a universal constant. It's like the ultimate rule of the road, but for the entire universe, right?
Yeah, and you're right. That constant speed of light, it leads to some really strange, really bizarre consequences, like time slowing down, lengths contracting in the direction of motion, and we chalk these up to the very fabric of space-time.
Exactly. But Close, he questions whether this, specialness of the speed of light, if that's really the whole story. Maybe, just maybe, it has more to do with how we measure space and time rather than some inherent property of light itself. What do you think?
And it begs the question, could we have a theory of relativity where light isn't the star of the show?
Okay, now that's where it gets really interesting.
Yeah.
To kind of get the point across, Close uses this analogy, and it's brilliant. Imagine a world, okay, where submarines, they use sonar to navigate, not just like see, but to measure distance and time.
Okay.
So say they have these sonar clocks that measure time based on how long it takes sound waves to travel underwater.
It's such a good way to make us really re-examine our assumptions because we just take it for granted, right? That our clocks tick at a steady rate.
Totally.
But what if that rate is dependent on something else? Something fundamental to how we measure?
Exactly. So picture this. In our submarine world, if they based all their physics on these sonar measurements, they would actually end up with those same bizarre Lorentz transformations that we usually think are tied to the speed of light.
Yeah.
Time dilation, length contraction, it all looked very familiar.
And for those who don't know, Lorentz transformations basically describe how space and time get distorted at speeds approaching the speed of light.
Right.
And Close is suggesting that maybe we're seeing those transformations not because of the nature of space-time, but because of how we're measuring it.
So it's not necessarily that the speed of light is the only speed that could lead to relativity. It's more that our material world, the stuff we're made of, could be fundamentally intertwined with something moving at that speed.
Right.
Making our measurements line up with how light behaves.
Exactly. It's almost as if we're dancing to the rhythm of a cosmic waltz, and light just happens to be the most obvious instrument in the orchestra.
So then, Close, he takes us even deeper down this rabbit hole.
Oh, yeah.
He asks, what if matter itself is actually made up of waves? Waves that travel at the speed of light.
Wow.
Not just behaving like waves as, quantum mechanics suggests, but actually being waves.
Yeah. And he's not just throwing out this wild idea here. He's building on some well-established physics here, specifically something called soliton waves. Have you heard of those?
I have heard of soliton waves. Remind me.
Yeah. So these are these little packets of energy that can hold their shape and travel over long distances.
Okay.
So think of a pulse of light that can just kind of keep going and going.
Right. Like a tsunami, but for light.
Exactly. Yes, exactly. So imagine these soliton waves, and they're zipping around at the speed of light. But here's the thing. They're not moving in just a straight line.
Okay.
They have this internal circulating motion, like tiny little whirlpools of energy.
Okay.
And that's really the key to understanding this whole model. He's suggesting that what we perceive as the movement of a particle is actually the overall movement of this entire soliton wave packet.
So so imagine it's like a tiny tornado of energy hurtling through space.
Yes.
At the speed of light.
Yes, that's a great way to think about it.
But if everything is always moving at the speed of light, then how do we end up with slower speeds, the speeds that we see in our everyday world? You know what I mean?
Yeah, that's a great question, and it all comes back down to geometry.
Okay.
Remember that internal swirling motion. That's what creates the appearance of slower speeds from our perspective. It's like that soliton is always taking this slightly roundabout path, even though its internal energy is always moving at the speed of light.
This is blowing my mind.
Right.
Okay. But there's an elegance to this. There's a strange elegance.
Oh, absolutely.
So how does this wave-based view of matter line up with, like, one of the most famous equations in physics, EMC2?
Ah, yes.
The one that basically says that matter and energy are two sides of the same coin.
Yeah, and that's where his model, I think, really shines because, so remember how we talked about the soliton having both, right?
Right.
Translational motion, that's what we see as particles movement.
Okay.
But it's also got that internal circulating motion.
Right.
So Close demonstrates that if you apply, good old Pythagorean theorem
Right.
to these different components of the wave's motion, you get
Don't tell me.
EMC2.
Oh, wow.
Yeah.
I never would have guessed that.
Sure.
It's such an elegant, that is a really elegant connection. So you're telling me that Einstein's iconic equation, this equation that revolutionized how we understand the universe, that just naturally emerges from the geometry of these soliton waves.
Yeah, pretty much. It's pretty amazing. And it gets even wilder. It gets even more mind-boggling when you start to think about how these ideas connect to the quantum world.
Oh, no, you're going to bring up quantum mechanics now.
Oh, yeah.
The even weirder, the even fuzzier world of quantum mechanics.
That's the one.
The one where, particles can be in multiple places at once.
Exactly.
And caps can be both alive and dead.
It's weird. It's a weird world down there, but what's really cool is that Close's wave-based view of matter, it actually lines up surprisingly well with some key aspects of quantum mechanics.
Okay.
Like the Dirac equation, for instance.
Okay, the Dirac equation, now just to make sure I'm following along, what is that again?
So think of the Dirac equation as like the quantum version of EMC2, but it's specifically for electrons.
Okay.
And get this, Close's model actually gives us a new way to interpret the Dirac equation.
Okay, so instead of it just describing the probability of finding an electron in a particular place, it could actually be describing the soliton waves of energy that make up the electron itself.
You got it. It's like he's building a bridge between relativity and the quantum world.
That's huge.
Yeah.
Two things, two realms of physics that we've never been able to unify. And he's like, I'm just going to casually stroll across.
Exactly.
This is like a paradigm shifting idea. This could change how we understand the universe.
It could.
At the most fundamental level.
That's...
But it also brings up so many more questions. So we've gone really deep on this idea that matter itself could be made of waves traveling at the speed of light.
It's a mind bender, isn't it?
It really is. But if relativity isn't about light having some special unique speed, then why is light still the star of the show when we talk about relativity? Seems like we're back to where we started.
Yeah, you bring up a really good point. And what Close argues is that since, if his hypothesis is true, material objects, we're all just made up of these light speed waves. Our very measurements, they just naturally align with how light behaves.
So it's almost like we're using light speed messengers to measure other light speed messengers.
Exactly. Yeah, our whole frame of reference, the way we perceive space and time, it's inherently tied to the speed of light.
And not because it's some magical speed limit, but because it's woven into the very fabric of matter itself.
Exactly. That's the point. And here's where it gets really wild.
Oh, no.
Okay. If that's true, then there's a possibility that there are other types of waves out there.
Okay.
Waves that don't travel at the speed of light, and therefore don't follow the same rules of relativity.
Hold on. Other types of waves that don't follow the same rules.
Yeah.
What would those even look like? Can you give me an example?
Well, Close mentions gravity waves.
Okay.
Those ripples in space-time caused by, huge events in the universe. We've only been able to detect those very recently.
Right.
And there's still a lot we don't know about them, but imagine if it turns out gravity waves, they have their own speed limit, one that's different from the speed of light.
Whoa. So you're saying there could be different versions of relativity?
It's possible.
Depending on what kind of wave you're talking about.
It's a really exciting idea.
The universe just got a lot bigger.
It did, and it just highlights how Close's ideas aren't just about rethinking what we know. They're about opening up entirely new avenues of exploration. So, to recap, maybe relativity isn't about a special speed at all.
Right.
Maybe it's more about this really deep connection between matter, light, and the very way we make sense of the universe. It's not just that the speed of light is constant.
Right.
It's that everything in some fundamental way is made of that constant.
And if we can wrap our heads around that idea that matter itself is fundamentally like wave-like, what does that tell us about what it means to exist in this reality? What does it even mean for something to be a wave and a particle?
Right.
What does it tell us about fields and forces, even the very fabric of space-time itself?
Big questions. That's what makes this so exciting.
Yeah, it's like we've stumbled upon a hidden doorway in physics.
Yeah.
And it's led us to completely uncharted territory.
Exactly. And, like any good adventure, our deep dive today, it leaves us with more questions than answers, but those are the best kind of questions, aren't they?
They are. They're the questions that keep us up at night.
Exactly.
Pondering the mysteries of the universe. So, if matter really is just this, like, dance of waves, what does that tell us about the music of existence itself?
I love that.
That's something to think about. Until next time, keep diving deep.